These are the first half of the notes for the chapter 8 for APC. So in this particular chapter now we're going to talk about circular motion, so moving in a circle. So motion in a circle, again, velocity can be calculated distance over time, but when you're moving in a circle, the distance is 2 pi r, and the time to go around once around the circle is what we call a period. Since it's a specific time, we use a capital T symbol for that, as shown right here. But it's just the time it takes for objects to complete one rotation. And so we get that the velocity of an object moving in a circle is just 2 pi r over big T. Again, it just starts from here. It's just tailoring it to the fact that we have a circle. And objects don't like to move in a circle. They will go in a straight line if they can. So here's a question. A ball on a string is swung in a vertical circle. The string happens to break when it's parallel to the ground and moving up. So the ball is moving this way. What trajectory does the ball follow? The only thing keeping it moving in a circle is the string, and so it will go straight. So C is the correct answer here. So when we're moving in a circle, even if we keep a constant speed of, for example, 5 meters per second or 20 meters per second, when you're moving in a circle, your direction is always changing, and therefore you are accelerating. And we call that centripetal acceleration. The symbol is A with a little c. And it just means center seeking, because in order for an object to move in a circle, it has to get pushed toward the center of that circle. And so it's caused by just the changing direction of an object moving in a circle, and here is the equation for that. I believe this is on your formula sheet, v squared over r for centripetal acceleration. It is an acceleration, so it has the same units that we've been using for acceleration before. So, knowing we've got v squared over r, a fighter pilot makes a turn and pulls 8g. This just means that it's 8 times gravity. So it's 8 times stronger than gravity. If a pilot makes a second turn at the same speed but with a larger radius, then do you know about the centripetal acceleration? So if we think about, go with pen here, v squared over r, and we play the what if game here. So if we have the same speed, so we're not changing this, so we just keep that as a 1, but we're making a bigger radius, then we're going to have a smaller acceleration because we've got a bigger number in the denominator. And so we'd have c less than g. Okay, and if the radius of the second turn is twice as large, specifically, so that means that we're essentially going to cut that acceleration in half, then we'd get 4 g's. So he makes the turn and pulls 8g. If he wants to make a second 8g turn while going faster, going faster is going to make his acceleration bigger, but I want the same, so the radius is going to have to be smaller. And now we're saying, okay, if he's going twice as fast for the second turn, now here's where again, v squared over r. So we have to think about, we're going twice as fast. So v is basically 2. 2 squared is 4. And so the radius has to be 4 times bigger in order to make the same acceleration. And so if we start off with 5 kilometers, we need 4 times that. And so we're going to need 20 kilometers. Okay, and wherever there's an acceleration, there is a force. So F sub c, it's the force that causes that acceleration. And so we have, again, our just F equals ma, but then when a equals v squared over r, we can substitute that in. It is a force, so it is measured in newtons. It points to the center of the circle, just like the acceleration does. But it's kind of interesting because the centripetal force is not a separate, unique force. We don't ever identify a force touching an object that is F sub c because it doesn't technically exist. It's actually some other force, friction, tension in a string, that causes the object to stay moving in a circle. And so, like I said, we don't really identify F sub c as a force. It's more of a category. It's a general, whatever force keeps moving in a circle. So for uniform circular motion, the net force always has to point to the center of the circle. And then you probably have heard this term before. Centrifugal or centrifugal force is used a lot in the popular media, but it doesn't exist. It's not a real force. It is used to describe the feeling of being thrown or pushed outward as you move in a circle. Because as you move in a circle, that's how you feel like you're getting thrown out to the outside. But we said that centripetal force pushes toward the center. This feeling of being thrown or pushed outwards is just inertia. It's just Newton's first law. Your body does not want to go in a circle. It's trying to go straight. It's trying to stay exactly what it was doing. And it's the centripetal force pushing you toward the center that keeps you moving in that circle. So we have an example here. I believe this is the last slide of doing these calculations. So you have a 2,500 kilogram car traveling at 40 meters per second around a curve of 50 meters. The car's centripetal acceleration, so if I do v squared over r equals a. So I'm going to have 40 squared over 50 equals 32 meters per second squared. So there's the acceleration. The centripetal force is just mac. So 2,500 times 32 gives me 80,000 newtons. So that's how much force I need to stay in the circle going that fast. And then the question here, what is causing the centripetal force? The only thing that can be causing it right at the moment is friction. It's friction, and I better have that much friction, because if I don't have that much friction, I'm not staying in that. I'm not continuing to move in a circle. I will go in a straight line. And that is the end of the Chapter 8 notes. So these are the second half of the Chapter 8 notes, and we want to continue talking about kind of circular motion, and then we're going to also introduce banking, when we essentially throw the circular motion on a curve. So what is the maximum speed of a 1,500 kilogram car can make without sliding around an unbanked curve of radius 50 meters if the coefficient of friction is 1.0? Alright, so here, remember that the centripetal force, Fc, equals some other force. In this case, it's going to be friction that keeps the car on the road. So if we substitute, if I've got mv squared over r equals mu mg, the mass cancels out, and so I can rearrange this for v is going to be the square root of mu rg. And so if I plug the numbers in, I've got 1, I've got 50, and then I have 10. So essentially the square root of 500 gives me 22.4 meters per second. And okay. So here's another example. A car with a mass of 1,350 kilograms traveling at 55 kilometers per hour when it encounters a curve with a radius of 40 meters. What's the minimum coefficient of friction needed to keep the car on the road? So first thing we need to do is change this to meters per second. I won't go through the whole process. It comes out, it's 15.3 meters per second. So it's the same situation we had in the last example. We've got mv squared over r equals mu mg. Again, it's friction that's keeping the car moving in a circle. Masses cancel out, and so for this one, it wants to know what mu is. So mu is going to be equal to v squared over rg. So if I've got 15.3 squared divided by 40 times 10 gives me a coefficient of 0.58. And again, there are no units on the coefficient of friction. And then for the second part, if the pavement is wet and oily and we're reducing the coefficient of friction to 0.3, what's the maximum speed it can have? So we're going to use the same equation. It's just now we're going to solve for that velocity again, just like we did in the last problem. And it's the square root of mu rg. And so I'm going to have 0.3 times 40 times 10. And this is going to equal 11 meters per second. So we have to slow it way down if we're going to reduce the friction. Okay, so now what do you do if you don't want to rely on friction? Well, you have to bank the road. And so this is not the money kind of banking, but when a car runs a flat curve, it relies basically on friction alone to keep it on the road. And so the radius has to be fairly large to allow higher speeds without sliding. If I want the radius to be smaller and still allow the high speeds, like on an interstate or a racetrack, the solution is to bank the road at an angle. And what that does is that a component of the normal force helps keep the car on the road. So here's an example. I've got a banked road free body diagram. So here's my car on the incline. I'm looking at essentially at the back end of the car, so it's moving into the slide. And as it goes around this circular track. So I have the weight pulling straight down, I have the normal force perpendicular to the surface, and what I'm interested in is what is the force that's pointing to the center of the circle, because that will be my centripetal force. And so for here, I need to line up things that are just perfectly vertical and horizontal, which means it's the normal force that needs to be split into components. And so if I split the normal force into components, this is the angle of the incline. And so this is the side that is adjacent, and that's why that's n cosine. And then we have an n sine component. And so here, if the centripetal force is equal to this, then the car will stay put. It won't start sliding up the incline and going straight. So notice that you've got n sine of the angle is going to equal this centripetal force, and you've got n cosine equal to the weight, or mg. So for this particular type of problem, we're going to set those two equations equal. So let's just go with green. So I've got mv squared over r, the centripetal force, equal to n sine of the angle, and I've got n cosine equal to mg. So I'm going to use this equation and solve it for n. So that's going to be mg divided by the cosine of the angle. So what I'm going to do is I'm going to take this and I'm going to put it in up here. So when I do that, I end up with mv squared over r equals, and then I'm going to have mg sine divided by cosine. And a couple cool things happen here. The masses cancel, so the mass doesn't matter again. And then this is equal to the tangent of the angle. So now if I'm rearranging for the velocity, it's going to be the square root of RG times the tangent of the angle. And so now if I plug numbers in here, I've got 50 times 10 times the tangent of 15. And this is going to give me 11.6 meters per second. Okay, so the big thing again is just looking at setting these two equations. These are the two equations from the free body diagram, and we just solve one for the normal force and plug it in. And we end up with sine over cosine, which is equal to the tangent. So the other thing is, if I have objects that are moving around a planet, for example, in a circular orbit, what keeps it in the circular orbit is gravity. Or gravity is the acceleration that keeps it in that circular orbit. So we have v squared over r. And so if we want to find then the velocity of how it's orbiting, it's the square root of rg. The other thing is, if we're moving objects in a vertical circle, like if we're swinging a bucket of water, there'll be some velocity. So here would be a normal situation where you have a normal force because this object is pushing against the curve, and so there is a net force here. This would be a slightly different example. So now this is like the top of a loop-de-loop, so you're going upside down. Weight's pulling you down, but essentially at a magical spot, there is no normal force here because we are just not touching whatever it is we were touching before. So here's an example where if gravity is too big, then the water will fall out of the bucket. But here's the situation I was talking about. At that very top, if we've hit that critical speed, the normal force here will actually be 0. And so the only force that's pointing to the center and keeping this thing moving in a circle is the force of gravity. So that would apply to this example here. If a car drives over the top of a hill that has a radius of 50 meters, what maximum speed can the car have without flying off the road at the top of the hill? Well, if just before it flies off, or just as it flies off, there is no normal force. So the only forces that you have going on are, you have mv squared over r equals mg. Masses cancel, so if I want to find v, it's the square root of rg. And so if I plug the numbers in, I have 50 for r, I have 10 for gravity. Square root of 500 is 22.4 meters per second. And so that is the end of the Chapter 8 notes. So this is showing you how to deal with banking with friction. We did an example on the last part of the notes about banking without friction, and the idea is that if you have a car on an incline and it's going around a circle, that we need to find what the centripetal force is that's keeping that car moving that direction. So you have the weight, you have the normal force, but we need to know what force just goes straight in. And so we're assuming here without friction, you have to split the normal force into components. And so this becomes n cosine, and this becomes n sine. And so you ended up with Fc equals n sine. In other words, mv squared over r equals n sine. And if you look the other way, n cosine equals w. So you have mg equals n cosine of the angle, and so n would equal mg over cosine. And then you stick that in and substitute it in where n is, and you get mg sine over cosine. The m's cancel out, and you get v squared over r equals g tangent of the angle. And then you can find whatever pieces you're looking for. If you're looking for the velocity that you can have, if you're looking for the radius, if you're looking for the angle, you can rearrange to find those. So now let's add friction. All right, so now we're going to add friction. So again, we're going to have the weight. We're going to have the normal force, which will split into components. So I'm again going to have n cosine and n sine. And again, we're looking for the centripetal force that's going to pull this direction. Now, we also have friction. This car wants to slide up the incline, so friction is going to go down. But again, we need to split it into components. So if I put, friction will go this way. And so friction is going to have a component this direction and this direction. And so this is the side adjacent, so this is F cosine, and this is F sine. And so now if we look at the up forces, we have the weight plus F sine equals n cosine. And I'm going to replace some of this things, so I've got mg, and I'm going to move this to the other side, n, and I'm going to factor out an n here. I've got cosine minus mu sine. Basically, I just replaced f with mu n. So n is going to equal mg, and then I have cosine minus mu sine. So this should look pretty familiar to the no friction example with the addition of this piece. Because if we just look at mg over cosine is what we got for the normal force before. So now we need to look at what's causing the centripetal force. And so I have mv squared over r is equal to the normal force times the sine plus mu times the normal force times the cosine. Again, that's F. And so if I factor out an n again, so I get mv squared over r equals, factor out an n, I have sine plus mu cosine. And now I'm going to take this normal force that we found and stick it in here. So I get mv squared over r equals, and this is going to be mg sine plus mu cosine divided by cosine minus mu sine. And again, the mass cancels out, and you have this whole big mess that we didn't have before, where this whole piece used to be just the tangent of the angle. Now we've got, you can kind of see the tangent right here, but we've got these extra added pieces that come into play. So that's how you deal with banking with friction. And I think one of the problems you're going to look at today deals with banking with friction. So good luck.